Hello. In this video I want to discuss an example we talked about in class. We are given a function f of x defined as this integral. So we've got the integral from 0 to x of a function e to the t squared minus 1 over t squared plus 1. Now note that the integrand, in other words this function here that we are integrating, is continuous on the whole real line, and therefore our function f is defined on the whole real line, and moreover, due to the fundamental theorem of calculus, it is in fact differentiable on the whole real line. Now we want to make a rough sketch of the graph of f so that we have some idea of what this function looks like and how it behaves. Now to calculate any explicit or exact value for f, say calculating f of 2, would require us to evaluate a very difficult integral. So instead of trying to find exact values for f and then plotting these, we use the fundamental theorem of calculus to extract some information about the function, which will enable us to plot a rough sketch of the graph of the function. Now the first thing we can note is that we can in fact calculate at least one value of f explicitly, and that is f at 0. And by definition, f of 0 is the integral 0 to 0 of e to the t squared minus 1 over t squared plus 1 dt. And because we're integrating from 0 to 0, this integral is just 0. Now this is the only value for t we can calculate without having to evaluate a very difficult integral. Now to get a good idea of what the graph looks like, we start by calculating the critical points of our function. Now by the fundamental theorem of calculus, our function f is differentiable and its derivative is given by e to the x squared minus 1 over x squared plus 1. And for critical points we set the derivative equal to 0. Now we can note that e to the x as well as 1 over x squared plus 1 are both bigger than 0 for every real number x. Therefore the only term that can make the derivative 0 is that one, x squared minus 1. So that term determines whether or not the derivative is 0. So we have that the derivative of f is 0 if and only if x squared minus 1 is 0. Right? So we see that the derivative is 0 if and only if x is either minus 1 or x is 1. Therefore our function has two critical points, one at x equals minus 1 and one at x equals 1. Now that we found the critical points, we need to decide or need to investigate what happens to f at the critical points. In other words, we need to classify the critical points either as a local maximum, a local minimum, or as a saddle point. Now you'll recall that there are two ways of doing this, or at least two ways: the second derivative test and the first derivative test. Now we're going to use the first derivative test, which means we have to look at the sign of the derivative. Alright, so our critical points are at minus 1 and 1. So we need to know what is the sign of the first derivative on the interval minus infinity to minus 1, and what is the sign of the derivative of f on the interval from minus 1 to 1, as well as on the interval from 1 to plus infinity. So again, if we just recall what the fundamental theorem of calculus tells us about the derivative, right, it's that. Now the fundamental theorem of calculus gives us this as the derivative, and as we've noted before, both e to the x and 1 over x squared plus 1 are positive for all real numbers x. Therefore, the sign of the derivative is determined by that term. So, let's see. For x less than minus 1, well, in this case, x squared minus 1 is bigger than 0, and that tells us that the derivative is also bigger than 0. For x between minus 1 and 1, x squared minus 1 is less than 0, which tells us the derivative is likewise less than 0. And for x bigger than 1, x squared minus 1 is now again positive, which tells us that the derivative of f is also positive. So what have we got? Right? For x less than minus 1, the derivative is positive. So that means the function is increasing. So here our function is increasing. For x between minus 1 and 1, the derivative is negative. So our function is decreasing. And for x bigger than 1, the derivative is again positive. So the function is increasing. Right. So our derivative is positive, negative, positive. And from this we see what f does here at minus 1 and at 1. Right? At x equals minus 1, we have a local maximum. While at x equals 1, we have a local minimum. Yeah. So this tells us what the local behavior of the function f is. Now, to get a clearer picture of the whole graph of f, we need to look what happens as x goes to plus or minus infinity. So let's first look at what happens as x goes. Let's first look at what happens as x goes to plus infinity. Well, again, right, we write down the derivative, right, because we don't know what the values of f are exactly. So we only have this definition for f as an integral, and that integral is very difficult to evaluate. So we look at the thing that we do have some knowledge about, and that's the derivative. Now, we can rewrite this as e to the x times 1 minus 1 over x squared over 1 plus 1 over x squared, right? And we simply multiplied by 1 over x squared over 1 over x squared. Now the reason we do this is because now we've got a product of two functions and we know what these functions do as x go to infinity. Right? We know that as x goes to infinity, e to the x goes to infinity, and we know that as x goes to infinity, 1 over x squared goes to 0. And that tells us that as x goes to infinity, this whole thing, 1 minus 1 over x squared, 1 plus 1 over x squared, this is 1. Okay. So that guy goes to 0, to infinity, that guy goes to 1. So we see that the limit as x goes to infinity of the derivative of f equals infinity. And now we recall that we have a theorem. We have a theorem that tells us that if the derivative of a function goes to infinity as x goes to infinity, then likewise the function itself goes to infinity as x goes to infinity. Right. So now we have some information about what the function f does as x goes to infinity. The function f goes to infinity as well, so it blows up. Lastly, now let's look at what happens as x goes to minus infinity. Well, again, we look at the derivative. And as we saw a moment ago, we can write this as e to the x times 1 minus 1 over x squared over 1 plus 1 over x squared. Of course, this is valid only for x not equal to 0. And now again, we know what happens as x goes to minus infinity, e to the x. E to the x goes to 0. And just as before, as x goes to minus infinity, 1 over x squared goes to 0, which tells us that as x goes to minus infinity, 1 minus 1 over x squared over 1 plus 1 over x squared goes to 0. And from this, we can conclude that the limit as x goes to minus infinity of the derivative of f is 0. Now, what does this tell us? What conclusion can we draw from the fact that the derivative goes to 0 as x goes to minus infinity? Well, this may seem to suggest that the limit as x goes to minus infinity of f is some finite real number L. In other words, f has an asymptote. Is this true? Right. Well, it may be true for our function f, but in general it is false. And one can see this at the hand of a relatively simple example. So let's see. The fact that the derivative goes to 0 in general does not imply that the function itself has an asymptote. And the example, to see that this is so, is f of x equals ln x. Well, let's take absolute value ln x. Now, the derivative of this function is just 1 over x. So, the limit as x goes to minus infinity of the derivative is 0. But of course we know that the limit as x goes to minus infinity of ln absolute value x is infinity. Right? This is not any real number L. Right? So we see we cannot conclude from the fact that the limit of the derivative is 0 as x goes to infinity that the limit of the function is a finite real number, so that we have an asymptote. So that means we need to do a bit more work. So let's go back to our case. So back to our function. Well, there's a couple of things to note here. Firstly, that for x between minus 1 and 1, the derivative is negative, as we've seen before, which means our function is decreasing. And this tells us that f at minus 1 is bigger than f at 0, and we've calculated f of 0 to be 0. Right. Secondly, for x less than minus 1, we saw that the derivative is positive. And if we look at f of x, right, this is integral 0 to x, and let's just write derivative f of t dt, which we can write as f of at minus 1 plus integral minus 1 to x f prime t dt. Right. Now that one is bigger or equal to 0, that one is bigger or equal to 0, so the whole thing is bigger than 0. Right. So what have we got? We've got that for x less than minus 1, the derivative is positive, and f of x is positive. What does this tell us? Well, from this we can conclude that the limit as x goes to minus infinity of f is some real number L. And this L has to be bigger or equal to 0. Why is it bigger or equal to 0? Well, because f itself is bigger than 0. Now, this can be proven, although the proof goes beyond the mathematical machinery we have at our disposal at the moment. But we can get a bit of intuition for why this is true. So, let's draw a graph of our function. Well, not necessarily of our function itself, but any function that satisfies these conditions here, right? So f of minus 1 bigger than 0, for x less than minus 1, f is bigger than 0, and the derivative of f also bigger than 0. Right. So we start up here, right? Now, for x less than minus 1, the derivative is positive. So that means, as we move in the negative direction, the function values become smaller. So the graph goes downwards. But f is positive, right? So the values of f cannot go downwards indefinitely. It's bounded from below. So that means there has to be some lower bound here, some asymptote, some L, right? So intuitively this makes sense, and it can be proven, but the proof just relies on a bit of mathematics we haven't done yet. Okay, so now we are in a position to sketch our function. Right, so we know we start over here, f at 0. At 1, we have a local minimum. At minus 1, we have a local maximum, right? F of x goes to infinity as x goes to infinity, and f of x goes to some real number L bigger or equal to 0 as x goes to minus infinity. Right. So let's see. Right. So if we start down here at 0, now our graph moves downwards until it hits the local minimum. Right. And at this point now the derivative changes sign. The function starts increasing and it goes to infinity. On the other side, we move up towards the local maximum. We hit it, now the derivative is positive again, we go down, down, down towards some asymptote. L. Right. And there we have a rough graph of our function. Right, so we know what the shape of the function is, or the shape of the graph is. We don't know the exact values at any point except here at 0. Right, but for a qualitative understanding of the function, this is good enough.